Welcome to Opportunity Crude Management Seminar Series, an informative look at crude processing challenges. Disclaimers. The purpose of the OCMS series is to provide refiners with the latest information in processing opportunity or price-advantaged crudes, such as heavy sour oil, oil sand bitumen, light tight oil, and highly acidic crudes so that they can make better decisions in light of a volatile oil market. Opportunity Crude Management Seminar Series Video Number 8, Your Corrosive, Naphthenic Acids and High-Tan Crudes. As mentioned in our previous videos, certain crude quality and blending practices have caused concerns for refiners due to potential problems from cheaper crudes. Corrosion is one of two major problems refiners face when processing certain crudes and blends. It is estimated that corrosion costs U.S. refineries about $3.7 billion a year. According to the 100 largest losses by Marsh & McLennan companies, the refining industry suffered $2 billion worth of losses related to corrosion damage alone over the 5-year period from 2007 to 2011. These problems have led to an increase in demand for corrosion inhibitors in the United States, which is expected to increase to a demand worth $2.5 billion by 2020. Concerns over corrosion have also led refiners to incorporate corrosion detection in safety practices, and, according to Lloyd's Register Capstan, downstream sectors have invested in specialized studies to implement reliability-based mechanical integrity programs and to support risk-based assessment plans. This seminar will discuss corrosion caused by naphthenic acids in high-acid crudes, or HACs. Our previous video, A Lot of Problems, Fouling and Corrosion, Part 2, Corrosion, discussed corrosion in distillation towers caused by crude contaminants and sulfitic acids. For all intents and purposes, the terms high-tan crudes and high-acid crudes will be considered synonymous and will be used interchangeably in today's discussion. Today's video will have 10 sections: background on high-acid crudes and TAN, global supply of high-acid crudes, recent news on refining high-acid crudes, measuring TAN, mechanism of naphthenic acid corrosion, most affected areas by naphthenic acid corrosion in a refinery, desalting high-acid crudes, naphthenic acid corrosion monitoring and predicting, techniques to control naphthenic acid corrosion, and the conclusion. Navigate oil market uncertainty and supply disruption in refining at the 6th Opportunity Crudes Conference in Houston, Texas in the U.S. from October 22 to the 24th, 2018. The theme of the conference is Crude Disruptors, Accelerating Changes in Global Refining. Higher oil output and refining price advantage. Domestic light tight oil has benefited international oil majors and U.S. independent refiners in the first quarter, respectively, according to just released earning results. Unfortunately, the good news will end soon as the oil market is going to enter an uncertain time since the price rout in mid-2014. A dark cloud is forming as driven by two formidable forces, geopolitical risks and changing supply-demand fundamentals. Change is not new in the refining world, but disruption of crude sources could significantly upset overall refinery operations in terms of crude management, processing, and product quality and volume. Our attendees will learn from conference speakers and network with colleagues on how refiners can navigate present market uncertainty and crude supply disruption by devising better business strategies, finding ways to increase operational flexibility, and adopting new technologies to turn challenges into opportunities. As in our previous meetings, this conference is expected to be highly productive and rewarding because of excellent speakers, timely theme, well-organized agenda, and stimulating atmosphere to encourage exchange of ideas. 5 topical sessions in 2.5 days include: Session 1, Global Oil Market Outlooks, Geopolitics, U.S. Pro-Export Policy, OPEC Strategies, Peak Demand. Session 2, Challenges and Opportunities in Oil Trading, Exports, Imports and Infrastructure Logistics. Session 3, Crude Contaminants, Incompatibility, Blending Strategies Amid Changing Feedstocks. Session 4, Flexibility of Light Tight Oil Processing and Bottoms Upgrading to Make Products in Demand. Session 5, big data analytics and emerging adoption of Internet of Things in crude selection, management, and refining. In this celebrated biennial meeting, you will meet colleagues from many companies around the world. The Opportunity Crudes meeting from October 22nd to the morning of October 24th is coordinated with Crude Oil Quality Association's fall meeting, which will be held on October 24th and October 25th to benefit from synergy in serving our upstream, midstream, and downstream colleagues. To save up to $300 before June 1st, register today by visiting opportunitycrudes.com/Houston 2018. Here is a preliminary agenda for the 6th Opportunity Crudes Conference. Total acid number or TAN is defined as the milligrams of potassium hydroxide to neutralize the acidity of 1 gram of oil. A high-acid crude or HAC will have higher levels of naphthenic acids and thus a higher TAN value. These crudes are generally priced at a discount compared to conventional crudes. However, there is no consensus of an exact TAN value an HAC will have. This is because not all crudes with the same TAN number cause the same extent of processing problems. For example, even though a refiner may consider a high-acid crude to have a TAN value greater than 1.0, the nature of the sulfur compounds and acids present may cause corrosivity for a crude with a TAN value of 0.5. Generally speaking, most refiners prefer to process crudes with TAN less than 0.5 and have hydrocarbon streams with TAN less than 1.5. This seminar defines a high-acid crude or high-TAN crude as having a TAN value greater than 0.5. High concentrations of naphthenic acids have been implicated in many problems in the refinery. Commonly reported problems with naphthenic acids include corrosion, desalter glitches, fouling, catalyst poisoning, product degradation, and environmental discharges. HACs cause operational problems in units such as hydrotreaters, FCCUs, lube plants, and have an undesirable impact on wastewater treatment facilities, hindering compliance with environmental regulations. With refined products, diesel made from high-acid crudes tend to have a low cetane number. The various methods of managing corrosion from high-acid crudes include predicting corrosion behavior of crudes and their risk levels, monitoring and inspection to identify areas at risk of naphthenic acid corrosion and to verify effectiveness of control methods, and applying corrosion control methods. Globally, high-acid crudes are the fastest-growing sector of oil production. According to Pira Energy, production of high-acid crude grades reached 12.9 million barrels per day in 2015, which represents more than 15% of the global production. HACs are supplied from places such as California in the U.S., Brazil, North Sea, Russia, China, India and West Africa. Oil sands-derived syncrudes are also considered to be high-acid crudes. The trend of crude being heavier and more acidic is expected to continue despite the discovery of new sources of light, sweet crudes. However, light, sweet crudes are expected to remain in high demand due to limited processing capacity and demand for light products. Therefore, heavy, acidic crudes are likely to still be discounted due to supply. This table shows the properties of major high-acid crudes produced in North and South America, namely from Brazil, Canada, Trinidad and Tobago, the U.S., and Venezuela. A complete list of major high-acid crudes produced around the world is available on our strategic report Novel Strategies of Processing Price-Advantaged Crudes in a Volatile Oil Market. According to a S&P Global article in May of 2017 called Western European Refineries and Acidity in Crude Oil, in Europe, pressure to use cheaper crudes have led to an increase in the average acidity of crude being processed. The average TAN value of crudes from the North Sea has increased dramatically from the 1990s, with a peak average TAN value of 0.35 in 2005. In 2009, pressure to use discounted, acidic crudes have decreased intake of light, sweet crude by 193,000 barrels per day. Previously, refiners used light, sweet, and low-acid feedstock from the North Sea at their own refineries and exported heavy HACs out of the region. But in 2009, a drive to increase high-TAN crude processing has created the need for sophisticated refineries able to handle HACs. The closure of 1.9 million barrels per day of refining capacity in France, Germany, UK, Italy and other regions resulted from the inability to handle high-acid crudes. As mentioned previously, refiners in Europe are facing a challenge of increasing TAN in crude. The following table shows the TAN value, API gravity, and sulfur weight percent of some high-TAN crudes in Europe, which include Alba, Buzzard, Captain, Clare, Griffin and Harding from the UK and Grain and Hydroon from Norway. Multiple refiners around the globe have been processing higher TAN crudes. Brazilian Petrobras reported that the average TAN of crude processed in the company's refineries increased from about 0.3 in the early 1990s to about 0.6 in the beginning of 2000. Global supply of high TAN crudes from Chinese production is expected to increase. A Chinese refiner is also looking to process more HACs from Africa. Its refinery in Chinchu is able to process HACs such as Dar blend from Sudan. An Indian state-owned refiner is looking to increase gross refining margins by processing more high-TAN crudes. Recently, multiple refiners have made investments into upgrades that would allow them to process high-acid crudes. A U.S. independent refiner has invested $300 million into upgrading its refinery so it can run 100% heavy high-TAN crude before the end of 2017. A state-owned refinery in Angola is being expanded so it can handle domestic heavy, acidic crudes, such as Quito and Dahlia crudes. In Asia, refiners in India, South Korea, and Thailand have upgraded refineries to increase HAC processing. Although crude acidity is an important issue for refiners and TAN is widely used to denote relative levels of acidity, there are currently no satisfactory test methods for determining this quantity for crude oils. Two standards, which are regularly applied for crude oils, were intended for use for petroleum products and lubricants. ASTM D974 uses colorimetric titration and has a reproducibility of 15%. ASTM D664 uses potentiometric titration and has a reproducibility of 20 to 44%. A modified version of ASTM D664 which extracts a sample first using chromatography can be used to determine naphthenic acid number. Because ASTM D974 and ASTM D664 were both specifically designed for other petroleum products, results for one crude oil sample may vary among different laboratories. According to a study reported at the February 2007 meeting of the Crude Oil Quality Group, slightly different testing procedures and preparation steps led to significant variation in TAN value measurements of Devil's Tower crude, which ranged from 0.5 to 16.87 at 9 different laboratories. Still, ASTM D664 is considered to be a good indicator of whether a crude is high or low TAN. Therefore, it is recommended crudes deemed high TAN using ASTM D664 should be further evaluated for naphthenic acid content. To get more consistent results, refiners should avoid samples with additives such as defoamers or paraffin inhibitors and remove soluble material by washing the sample with water and drying it thoroughly. As mentioned previously, crude samples identified as high TAN should be tested for naphthenic acid content, which better relates to corrosivity compared to total acid number. Some methods suggested in literature include tests from Shell Global Solutions and Baker Hughes. There also have been work on finding alternative methods on measuring TAN. ExxonMobil has been working on a new, rapid technique using electrospray ionization mass spectrometry for determining both TAN and TAN boiling point distributions in crude oils. The Canadian Crude Quality Technical Association has been sponsoring research on a thermometric titration method as a replacement for ASTM 664. It has been reported that the TAN value results from thermometric titration have correlated with those using ASTM 664, and this technique is less susceptible to interference from crude components. It has been recommended that this method be approved as an ASTM standard. The term naphthenic acid often describes all organic acids and crudes. Generally, naphthenic acids have 10 to 50 carbons, up to 6 fused saturated rings, and a carboxylic group. While naphthenic acids are naturally occurring compounds in crude oils, increased amounts of naphthenic acids are often caused by the addition of naphthenic acid salts as flow improvers. The image on the right is an example of a naphthenic acid. Naphthenic acid corrosion, or NAC, is a non-aqueous corrosion process caused by naphthenic acids. The most common regions of NAC are high-velocity regions, such as distillation units. NAC usually occurs in temperatures of 430 to 750 degrees Fahrenheit or 220 to 400 degrees Celsius. At temperatures above 750 degrees Fahrenheit, NAC does not occur due to the decomposition of naphthenic acids. NAC is differentiated from sulfidic corrosion because it occurs in areas of pitting and impingement and in high-velocity regions. Naphthenic acid corrosion can occur with materials such as chromium-12, American Iron and Steel Institute 316, and stainless steel 317. Even though many sulfidic compounds are corrosive, they can form iron sulfide scale on surfaces, which forms a protective layer against NAC. NAC is complicated as it can be time-variant, localized, and difficult to predict. NAC frequently occurs in areas of the distillation unit, which include crude feedstock heaters, furnaces, transfer lines, feed and reflux sections of columns, atmospheric and vacuum columns, and heat exchangers and condensers. The method of attack and influencing factors of NAC are different for each of these regions. For example, the velocity of the crude plays an important role in the amount of naphthenic acid corrosion occurring in the preheat furnace tubes, but has almost no effect on the rate of corrosion in the vacuum column. Downstream of the distillation units, naphthenic acid is generally not a problem, as the acids have mostly degraded. There are three categories of acid corrosion in refineries. In general corrosion, the same type of acidic attack occurs all over the refinery in units and pipelines. This type of corrosion results in shutdowns. Localized corrosion occurs in a specific location in the refinery, and the nature of the corrosion is affected by the conditions in that location. Stress-based corrosion technically does not involve a corrosion process but instead involves a combination of acidic attacks and stress that create cracks in metals. The following table shows how various factors, which include velocity, temperature, degree of vaporization, turbulence, naphthenic acid boiling point and concentration, and sulfur type and concentration, impact naphthenic acid corrosion rates in four areas: furnace tubes, transfer lines, vacuum column internals, and side cuts. Desalting is more challenging for HACs compared to traditional crudes due to their high densities, viscosities, and salt contents of HACs. These properties degrade desalter performance by making separation of the oil and water more difficult. Also, precipitation of the asphaltenes commonly found in HACs combined with high naphthenic acid content promotes the formation of stable water in oil emulsions called rag layers. This leads to high retention of oil in the brine water and increases the difficulty of salt removal at the desalter outlet. It is essential that the desalter is equipped with the means to detect and monitor rag layers so that they can be properly controlled by chemical injection. In many cases, an older desalter unit must be replaced with one equipped with new technology in order to handle HACs. There are two purposes of corrosion monitoring. The first is to identify problem areas where action needs to be taken, and the second is to ensure that prevention and mitigation procedures are being applied effectively. Methods to detect corrosion are described in the publication the NACE Technical Committee Report 3T199. These methods can be divided into three broad categories: inline metal samples for measuring corrosion rates, measurements of metal thickness, and detection and/or analysis of corrosive agents and corrosion products. Continuous corrosion monitoring may be applied to support risk-based inspections, to optimize the application of corrosion inhibitors, and to assist in crude selection. In combination with chemical inhibitors, it can be a less expensive option than upgrading metallurgy. Payback time can be just a few weeks, and the monitoring may be intrusive or non-intrusive. Intrusive monitoring involves local measurements and is most useful in cases where corrosion is uniform. Here is a non-exclusive list of current commercial monitoring techniques. In contrast to intrusive monitoring, field signature monitoring or FSM is a non-intrusive method that detects localized corrosion such as that produced by naphthenic acids. The resolution of FSM can be within 0.1% of wall thickness. This sensitivity allows for finer control over dosage of chemical additives. Emerson Process Management provides its ROCS corrosion monitoring solutions for both intrusive and non-intrusive monitoring. PermaSense is another source of technology for continuous corrosion monitoring. The company notes that its remote monitoring systems have utility in crude selection. Short-duration test runs of a potential new crude for a refinery can be applied to establish the corrosion rate associated with its use. This enables the refinery to identify a chemical treatment strategy that would enable it to process the crude on a continuing basis. Sensor Networks offers precision, fully digital ultrasonic wall thickness measurement systems coupled with wired and wireless data backhaul that enables semi-permanent, easily deployable corrosion monitoring systems. Despite the complex nature of naphthenic acid corrosion, there exist a number of advancements in the development of methods to predict where NAC may occur. Currently, modified Meconomy curves are applicable for low-tan crudes, but for HACs, risk-based inspection, or RBI, as provided in API Publication 581, provide guidance by identifying the likelihood of equipment failure due to corrosion and ranking the impact of these failures on refinery operations. A software package by Equity Engineering Group implements RBI for quantitative fitness for service analysis or materials evaluation. Other commercially available models include Predict Crude 2.0 from Honeywell, which uses crude assay data to analyze and predict crude corrosivity in CDU and VDU columns and piping systems, and Pathfinder from Nalco Champion, which assists in determining environmental factors that affects the conditions in which corrosion occurs. To mitigate corrosion from NAC, there are a variety of measures refiners can take. These measures include blending to reach a target tan value, upgrading materials via metallurgy such as adding molybdenum to stainless steel to produce alloys resistant to NAC, process operations, chemical inhibition such as the use of phosphorus-based corrosion inhibitors and naphthenic acid modification and/or removal. Depending on the refiner's strategy for crude selection and requirements for risk management, a combination of upgraded metallurgy and chemical inhibitors is often used. The combination of the two is a flexible method where upgraded metallurgy would be used in areas at most risk of corrosion and inhibitors are used elsewhere as needed. Perhaps the cheapest way to avoid NAC from high-tan crudes is to blend them with crudes that have a lower acidity. This method lowers the amount of discounted crude, such as high-tan crude, that can be processed. Blending to reduce acidity is considered to be a somewhat reliable method to control NAC. Usually, HACs are blended with a less acidic crude to achieve a blend with a tan value of less than 1.5. Blending to a target tan value can reduce corrosion by reducing the amount of naphthenic acid. Additionally, if the low tan crude to be blended with is lighter, wall shear stress is reduced, which lowers corrosion. Finally, the low tan crude may have a higher level of sulfur, which can inhibit NAC. Here is an example of blending to lower tan. A 100% highly acidic crude slate of hydroon, grain, or troll, which are crudes that all come from the North Sea, can have its average tan lowered if low tan crude were to be added. For these crudes specifically, troll would require less than 30% of 40s to be added to meet acceptable levels. but the higher tanhydrine and grain would need to be blended with more than 85% of low-tan crude. Blending to lower acidity is a linear process. Upgrading refinery equipment and surfaces using metallurgy may provide the best protection in the long term, but is a very expensive measure to take and would only be economical if HACs are continuously processed for an extended period of time. Steel is commonly alloyed with chromium and molybdenum to protect against NAC. According to speakers from Shell Global Solutions at a NACE conference, the amount of chromium made to exceed 18% to effectively protect against NAC. According to SET Laboratories, steel molybdenum alloys that can effectively protect against NAC are 316 stainless steel with at least 2.5% molybdenum or 317 stainless steel with at least 3.5% molybdenum. In general, NAC can be controlled by lowering temperature and charge rate as long as the performance and throughput of the distillation units are not degraded. The amount of naphthenic acids left in vacuum resids depends on temperature in the distillation tower as seen in cases from Chevron and Valero. Imperial Oil has stated that atmospheric columns that run at high temperatures tend to have less problem with acids in the resid. Exxon Research and Engineering has developed the Materials Envelope Statement, a document that provides guidance on how to avoid process changes that cause corrosion. Corrosion inhibitors used for NAC are generally amine or phosphorus and/or sulfur-based chemical additives that protect metal surfaces from corrosive attacks. The type of corrosion inhibitor that should be used depends on the strength of the acid. For weak organic acids, the most cost-effective method is to use more filming amine or one that is more tenacious. Additional inhibitor may be needed for naphthenic acids in lighter fractions, such as gas oils, for which non-volatile inhibitors do not provide protection. Because corrosion inhibitors are considered to be a costly remedy, they should only be used as needed or as a stopgap measure until a scheduled shutdown. Here is our sponsor's experience. OCMS Seminar 1 discussed crude column fouling resulting from addition of thermally unstable phosphate esters used to control corrosion from refining high-tan crudes. Phosphorus deposits can result from thermal decomposition of the corrosion inhibitor. These decomposition products usually settle out in column trays and can lead to formation of hard deposits that can foul and plug the column. According to Dorf et al., Desalting is a breakthrough in corrosion science that allows for safe and reliable refining of high-tan opportunity crudes, reduced risk of phosphorus fouling and more effective passivation and ongoing corrosion protection can be achieved with up to 80% less phosphorus than competitor HTCI products. Desalting is different than any other commercial phosphate corrosion inhibitor. It is an ethoxylated triester with unprecedented oil solubility, thermal stability and is non-acidic. Desalting reduces risk of phosphorus fouling and increases corrosion protection by feeding up to 80% less phosphorus than competitor products, delivering more soluble phosphorus to fortify the protective iron sulfide scale, building a more tenacious iron polyphosphate scale and decreasing phosphorus dosage to maintain protection. Desalting is changing refiners' perspective on the use of phosphate ester corrosion inhibitors. High-tan crudes contain a higher level of contaminants and have an increased complexity of contaminant removal which may decrease desalter efficiency resulting in decreased throughput, increased water treatment costs and may also increase the rate of fouling. Dorf et al. Has invented a new category of adjunct desalter chemistry called reactive adjunct chemistry that offers step-change improvements in desalting performance. This new technology offers a low-cost way of expanding desalting capacity and increasing contaminant removal for desalting limited refiners. Adjunct chemistry refers to the use of a secondary chemistry to supplement the primary emulsion breaker. This patent-pending technology works by reacting with contaminants that are antagonistic to emulsion breaking to improve speed of emulsion breaking and rag layer control, which increases desalter efficiency without capital investment. With a tighter oil-water interface, the brine quality is dramatically improved, resulting in a reduction in slop oil generation and its associated reprocessing costs. More efficient contaminant removal increases the speed of emulsion breaking and improves crude dehydration. The speed of the emulsion breaking chemistry is a critical variable for rag layer control. Reactive adjunct chemistry adds desalting capacity, which can increase the use of high-tan crude and improve refining profitability. Another category of methods to protect against NAC is to modify or remove acidic components. The use of neutralization agents such as caustic or sodium hydroxide converts naphthenic acid to sodium naphthenate. Decarboxylation removes the acidic component of naphthenic acids through the use of high temperatures and other means. Hydrotreating is used to reduce the acidities of corrosive compounds. Finally, corrosive components could also be removed using extraction. These methods have pros and cons, and multiple patents have been developed to make improvements on these methods. This table summarizes the advantages and disadvantages of the various naphthenic acid control methods that we discussed. Except for crude blending, the rest of these control methods have significant capital costs and/or operating expenses. However, like the use of caustic injections, crude blending may result in fouling and other issues. Refiners who need to recover naphthenic acids may wish to avoid methods like thermal decarboxylation and hydrotreating that destroy them. When selecting a method to use, it is important to determine the operational and economic pros and cons. Refiners and companies have taken steps to reduce corrosion. Chevron has been reported to have a target tan value less than 1.5 in atmospheric column side cuts. BP has blended Californian crudes having tan values up to 2.5 with lower tan crudes to achieve a target tan of 0.5 or less. The company indicated at a past NPRA Q&A session that this procedure has been used in a unit without high alloy for 5 years and had no indication of corrosion. Baker Hughes has implemented a program called SmartGuard, which combines chemical inhibitors, unit surveys, and monitoring to reduce NAC. Nowadays, crudes are becoming more acidic, as seen in North Sea production. These crudes are often attractive to refiners due to their discount compared to conventional crudes. Refiners should ask, are they ready to handle HACs? Refiners could potentially use models to predict corrosion, but it is important that refiners monitor operations to not only identify problem areas but also to determine if control measures are effective. Methods to control corrosion involve managing process operations, refinery upgrades, and the use of chemical additives. Refiners must consider the pros and cons of each method. With the right steps, refiners can reap the economic benefits of high-tan crudes. Thank you very much for watching our video. Please join us in March for our next seminar, video number 9. Don't take it lightly, challenges in processing LTO. Thank you to our sponsor Dorf Katal. Sponsorship opportunities are still available for the rest of the seminar series. Please contact Matt Wonder at mwonder@hydrocarbonpublishing.com to sponsor a future video. Sign up today to receive our quarterly technology newsletter, Worldwide Refinery Processing Review. Since it was launched in 1998, the review has become the most authoritative and comprehensive publication of the latest refining technologies around the world. The review monitors commercial technology developments and competition, plant operation improvements and troubleshooting, and R&D trends for all processing units, from the front end to the back end, in a single source. Each issue covers 2 technology topics with the following sections: market and technology trends and opportunities, state-of-the-art technology, plant operations and practices, refining R&D alert, worldwide installed capacity, recent construction activity and completed construction projects, latest refining technology developments and licensing. As shown in the table, this year's subscription will cover 8 topics, 2 in each quarter, apart from an annual subscription of the review. Individual quarterly issues and individual technology topics are also available for purchase. For more information, contact us at review@hydrocarbonpublishing.com. Here are upcoming crude oil quality events. Your comments are appreciated. Please send your comments to info@opportunitycrudes.com so we can enhance the value of upcoming seminars. Disclaimers.